Swayam Prabha. Digital India. Educated India.
Phi or whatever. So this is going to be my power factor angle phi. So the bottom line is, if I try to fire my AC voltage controller below phi, an angle below phi, I lose control. I don't have control because the inductance will anyway push the current until phi. The current is going to be pushed until phi, whether I like it or not. So if the current is continuing until phi or pi plus phi, whatever, I am really not going to be able to say that one device will go off before I fire the other device. That is not going to happen. So we will get control. So control of the output voltage is possible only if alpha is greater than phi, where phi is the power factor angle. So this is one of the criteria that's very, very important for the control of any of the single phase equipment if I want to have a control over the voltage. Fortunately, probably for a single phase induction motor, although the inductance is somewhat larger, we will generally not control it below 45 degrees or 50 degrees of firing angle. So we will always have the range, because the power factor angle will roughly be about 50, 60 degrees. So we will only have the control range from 50 degrees until 180 degrees in the single phase induction motor case. And we will not go until 180, because if we go until 180, the motor will not get any voltage. So we will not generally go until 180, but we try to limit the range of the firing control only from power factor angle phi until whatever is the maximum firing angle that could be fired. That is the way normally it is done. And invariably, the firing of rectifiers or AC voltage controllers will be synchronized with whatever is my incoming supply. So normally, the firing circuit will work in such a way that I first take the sinusoid from the supply itself by using a potential transformer, which will be like a step down transformer. So from 230 volts, it will step it down to 3 volts or 2 volts, right? So that kind of a stepping down action we have to do. So this will be done with the step down potential transformer. So it is essentially as good as having an open circuit on the secondary side. It is like no load test on a transformer. Similar condition will exist here. I will not connect any big load, right? And it will be rated for 1 volt ampere or even less. Very, very small volt ampere rating. So this sinusoid will be actually given to a comparator. Operational amplifier, what you did in ELL 100, right? The same kind of operational amplifier in open loop condition, when we use it as a comparator, to plus we may give this and the minus may be grounded, right? If we do that, what we get here will be a square wave, because whenever the plus terminal is at a higher potential than ground, I am going to get a positive saturation voltage, and whenever I am going to have the positive terminal, that is the sinusoidal voltage is less than ground, I will get a negative saturation voltage. So I can get a voltage here such that it will be somewhat like this. I am going to have a square wave coming out, right? Now this I can use probably with the help of a level shifter, or I can even have the plus VCC as 15 volts, minus VCC at 0, because there are operational amplifiers which work like that. So I don't even have to go until negative. But if I have negative also, I can use after this an integrator. Again an operational amplifier circuit. Right? So if I use an integrator, I will get the output to be something like this. Right? If I don't have any offset error, then this is how the integrator will work. Whenever I'm going to get a positive voltage constant, as I integrate, it will ramp up. And whenever I have a negative voltage, it will ramp down. This is how it is going to be. Right? Now this can be compared again. So integrator output is this. This can be again given to an op-amp comparator. Maybe I can make this as plus, and in the minus I can give some constant DC voltage. So if I know that the peak of this is going to be, let us say, 10 volts, for example, right? So if I give this constant DC voltage to be 5 volts, then I'm going to have the comparator output actually giving me, whenever my integrator output is greater than 5 volts, I'm going to have a positive signal. Otherwise, I will have a negative signal. So I would have the intersection of these two voltages. If this is 5 volts, for example, this is going to give me a signal somewhat like this. So this voltage, the constant DC voltage, is generally specified as control voltage, because this is the one which is going to decide the firing angle. If I have 5 volts, I will have exactly somewhere in the middle. So that is going to be about 90 degrees. If I am going to, because this whole thing is 180 degrees and this is another 180 degrees. So if I choose 5 volts, I will basically get a firing angle of 90 degrees. If I choose less than that, 2.5 volts, I will get 45 degrees, and so on and so forth. So this particular voltage, what I am using as the control voltage, decides the firing angle. So in good old days, when we were using only analog electronic circuits to generate the firing signals for all these things, we used to do this. Basically, all of us have done this to fire the thyristor circuits. Please note, the entire thing is now synchronized with the sinusoid. The complete thing is synchronized with sinusoid. So please note that the line commutated converters, be it rectifier, be it AC voltage controller, anything that works from an AC supply has to be synchronized with the AC supply, so that the firing signals go at the appropriate instance. Otherwise, you will not be able to designate this is what is positive half cycle and this is what is negative half cycle. So all these have to be synchronized with the input sinusoidal wave. So this is basically the firing signal generation that is done for AC voltage controller, for example. Right? So what I am trying to get at is, if I know the power factor angle, then I have to adjust the control voltage as per the power factor angle, so that I get control over the voltage. Otherwise, I will not get control over the output voltage. That's what I'm trying to get at. You get my point? So the control voltage plays a very vital role in deciding the firing angle, and the firing angle will be decided based on whether I require control. If I require control, it has to be greater than the power factor angle phi. Okay? So much so for single phase AC voltage controller. Let me try to now go in for the 3-phase AC voltage controller. His question was, this will generate firing signal only at alpha, then 2 pi plus alpha, and so on and so forth, 4 pi plus alpha, because of which it is generating the firing signal only for T1, not for T2. So if I want for T2, I might have to just invert this. This has to be completely 180 degree opposite, and then again I can use integrator and so on and so forth, so which will give me exactly the opposite of whatever I am getting, or 180 degree shifted waveform for the other one. Right? So all I can do is I can use one more comparator with plus here and minus here. That will do the job. Right? That's how it is. Okay? Now, let us now go over to the 3-phase AC voltage controller. There are several configurations, and one of the toughest circuits to analyze I have seen is the three-phase AC voltage controller. So let me take only one single configuration, which is the star connected configuration. Let me not go into delta. I am going to take only a star connected configuration. What I mean is, I am going to have the three-phase supply voltages connected in star and the AC voltage control devices also connected in series directly with this. And the load also I am going to take in star. Now I am going to take the load also exactly connected in star. Let me again start with resistance load. Otherwise, it could be more confusing. Let me start off first with resistive load. And let's say the numbering is essentially the same as what we did, 1, 4, 3, 6 and 5, 2. This is how they are numbered. So let me call this as VA, VB and VC with respect to neutral. This is the neutral of the source, whereas this is the neutral of the load. The load also I am showing as star connected. So that is neutral of the load. Now let me take a firing angle of 60 degrees. Let's see how the waveforms go, because I am just drawing right in front of you. Let's see how it goes. Okay. So I am going to take 60 degree firing angle. This is A phase. And I told you that the firing angle in this case is always calculated with respect to phase voltages. So I am going to have, this is the B phase. And this is going to be the C phase. Right? These are the three phase voltages. And if I am firing device number 1 at 60 degrees, that means I should have fired device number 1 here, because this is A phase, this is B phase and this is C phase. So I am firing device number 1 exactly at this point for alpha equal to 60 degrees. Right? So obviously I will have to fire device number 2 here, device number 3, device number 4, 5 and 6 should have been fired here. Okay? And 6, when it is fired, I should have B to be negative. Yes, B is negative. No problem. Right? Similarly, when I am firing 1, A should be positive. A is positive. That's not a problem. So, before 1 is being fired, 5 and 6 should have conducted together. Right? But now, when I am firing 1, let me start looking from this point. When I am firing 1, I am going to have actually 1 and 6 conducting together. So I am going to have the current flowing like this and it is going to return like this. Right? Will 5 conduct at this point? I have to check, because 5 can very well conduct if it is conducive. The situation is conducive. And 5 will conduct only if C phase voltage is positive. But C phase voltage is not positive, then I am firing 1, fortunately. If it is resistive load, that's why I didn't want to go into inductive load first. If it is resistive load, at this point, right, when I am looking at this point, I am not going to have clearly C is becoming negative from this point. So 5 cannot be conducting. I will have only 1 and 6 conducting. And when 1 and 6 are conducting, what I am getting as the load voltage is A here and B here. Assuming that My devices are not having any voltage drop. I'm getting essentially VAB across the two portions of the load. The third portion is inactive. The third portion is not even conducting. Only two portions are conducting. So if I may call this as load A, so let us say this is RA or ZA, whatever, ZA, ZB and ZC. Only ZA and ZB are active, ZC is not active. Am I right? So, if I try to look at what is the load voltage, load per phase voltage. What do I mean by load per phase voltage? If I look at what is the voltage across this alone or the voltage across this alone, that is the load per phase voltage. If I assume that it is balanced load, VAB is coming across ZA and ZB, and ZA and ZB are of equal magnitude. So I should have VAB by 2 across ZA, VAB by 2 again across ZB. Both of them have to be half of the total line-to-line voltage that is coming across each of the load. Now, I have to look for VAB. So, if I have to draw VAB, this is VA, VAB should have been 30 degrees leading. So, it must have become peak somewhere here and then it should come down something like this. At 30 degrees, it should have come down to 0. That is VAB. What I have drawn in pink color, that is VAB. Now, I have to say from this point onwards, I am going to have VAB, right? So, I will have VAB coming up maybe like this. That is the peak, I suppose, or close to peak, whatever, and I am going to have this coming down like this. This is how it is going to be. That is VAB by 2. What I will get will be VAB by 2. If I am drawing, so voltage across VZA, only voltage across ZA or impedance of A phase. That impedance across that, what is the voltage if I try to draw? This is the load per phase voltage. Per phase voltage of the load. So this will be VAB divided by 2. Is this clear? When I am having 6 and 1 are conducting, I have only AB voltage coming across ZA and ZB. So, voltage across individually ZA and ZB individually will be VAB by 2. Only thing is, you have to understand that this point is positive with respect to neutral, whereas this point is negative with respect to neutral, because the current is flowing towards that. So that is at a lower potential. Clearly, with respect to neutral, I will have one of them as positive, one of them as negative because of the current direction. As simple as that. Now, when 2 takes over, will 6 go away? That I have to check again. When 2 takes over, right? Whether 6 will go away, because 6 corresponds to B phase. Fortunately, B is becoming positive. So B will go away. That is, 6 will go away when I am firing 2 automatically. So I will not have 6 conducting. From this point onwards, it will be 1, 2. And 1, 2 is VAC. So in all probability, I will have a similar waveform because I will have again, this is VAC by 2. Because A phase and C phase will conduct now together. So if I try to draw the current for the next one, I should draw it as though the current is flowing like this through this. Now B phase is inactive for the next 60 degrees. Right? So I am going to have VAB by 2, then VAC by 2. After VAC by 2, I am firing 3. When I fire 3, whether 1 will go away? Yes, 1 has to go away. Because A phase is positive and it is beginning to become negative here. So obviously, when I fire 3, 1 is going away. So if 1 is going away, I will have only 2 and 3 conducting together from this point onwards. So I am actually going to have 60 degree interval. Here 6 and 1 will conduct. Here 1 and 2 will conduct. Here 2 and 3 will conduct. Provided it is a resistive load. I have not touched upon inductance. Now if 2 and 3 are conducting here, please note, I would rather have the current this way. The current will go like this and return like this. So this is for 2 and 3 and this is for 1 and 2 and this green is for 6 and 1. You get my point? So I'm going to have now 2 and 3 conducting. ZA is inactive. ZA is going to be inactive. So I would probably have this abruptly coming down and just keeping mum for some time. When 2 and 3 are conducting, ZA is inactive, completely inactive. So I will have literally 0 voltage, no voltage at all across ZA. Now I will have a similar one on the other side when 4 is conducting. 3 and 4 conducting will be VBA. So opposite of VAB. I will have VBA by 2. Similarly, when 4 and 5 are conducting, it will be VCA by 2. So in all probability, it will be a replica of this, but in the opposite direction, something like this. Right? Please note, we have taken a specific case of firing angle and resistive load. We have taken 60 degrees. If we had taken slightly earlier, for example 45 degrees, I would have fired one slightly earlier. When I fire one slightly earlier, C phase is still positive. Phi will not give up. Phi will say, I will also conduct because I am forward biased. Why not I conduct? As simple as that. You get my point? So whenever I am going to have the firing angle less than 60 for OR load, I will have sometimes 3 devices conducting, sometimes 2 devices conducting. So if I try to look for a firing angle less than 60 degrees, for example, if I fire 1 here, 2 here and so on and so forth, if I fire 1 here, please understand, phi will continue to conduct. Because phi will continue to conduct, I will have 5, 6, 1, all 3 of them conducting simultaneously. When I have 5, 6, 1, all 3 of them being connected to the load, it's as good as having a normal 3-phase supply. I hope you understand. It is not any different from having a 3-phase supply. When I have 5, 6, 1, 5 belongs to C phase, 6 belongs to B phase, 1 belongs to A phase. So when I have 5, 6, 1 conducting, it is as good as having a normal 3-phase supply connected to the 3-phase load. So only for that duration, where 5, 6, 1 will conduct, if I try to look at what is A phase voltage, what is B phase voltage and what is C phase voltage, it will be corresponding phase voltages itself. VAN, capital N I am talking about, VBN for the other one, VCN for the third one. Had it been an inductive load, what was going to happen for the same case? That's what I want to check. So if this is omega t for the same 60 degree firing angle. So this is going to be my one of the phase sinusoid. This is going to be the next phase, and this is the third phase. Let me take the same 60-degree firing angle. So I'm going to fire 1 here, 2, 3, 4, 5 and 6. We said earlier that when I was firing 1, automatically 5 will go away because it was having resistive load and C was becoming negative. So obviously that has to go away. But now I am having inductive load. If I have inductive load, the inductance stored energy is going to pitch in, definitely. That is not going to allow 5 to go out. Because the current is still flowing through the inductance, abruptly the current cannot come down to 0. So, even at this point where I am firing 1, I will have 5 continuing to conduct despite the fact that I am going to have C phase voltage coming into negative half cycle. So, at this point itself, I will have actually 5, 6 and 1, all 3 of them continuing to conduct. All of them will continue to conduct together. And how long 5 will continue? That depends upon essentially what is the kind of inductance value I am having in comparison to the resistance. If the inductance value is really dominating, I will have a good amount of energy, because of which I would have had probably 5 continuing even until here or whatever. But if the inductance stored energy is not too much, it will go closer and closer to the resistive load. Okay? So if I assume that maybe until this point 5 is continuing to conduct, then I should definitely assume the same way until this point 6 will continue to conduct, until this point 1 will continue to conduct, until this point, 3 will continue, 2 will continue to conduct, and so on and so forth. So I have shown different points where I may have continuation of conduction of the previous device which should have gone off, but it has not gone off because of inductance. So now, until this point, because 5, 6, 1 are conducting, if I try to look at what is the voltage across ZA, right? 5, 6, 1, when all 3 of them are conducting together, right?